When we apply a transform that undergoes a particular reaction, we tend to focus just on the specific changes that we want to occur. When we restrict our thinking in this way, we can encounter a synthetic trap. Right? And so what a synthetic trap is basically some factor we've temporarily overlooked that prevents the reactions from occurring in the forward direction as planned. So there's some factor we have temporarily overlooked that prevents the reaction from occurring in the forward direction as planned. Okay. Now, this happens to everybody. I still run into synthetic traps all the time. It's just because you get so focused on finding an answer that a lot of times you forget to evaluate the problems. So, for example, suppose our target here, right, which is an alcohol, must be synthesized from starting materials containing 3 or fewer carbons. And so we look at this and we say, okay, hey, look, I see a 1, 2, 3. There's the 2 and the 3, so I know that's an epoxide, right? And so we can make this epoxide here, or they've actually done it as a 1, 2, 3, right? So we're going to break it apart, and so we can start with this epoxide and this Grignard reagent, right? However, we encounter a problem when we try to do this, because when we look at this in the forward reaction, that Grignard reagent is a strong base. So when it reacts with the epoxide, it's going to attack that less highly substituted, just less sterically hindered carbon that we just talked about. And it's going to synthesize the wrong product, right? To produce the desired product, the nucleophile would have to attack the more highly alkyl substituted carbon of the epoxide. In section 10.7, we saw examples of nucleophiles attacking the more highly substituted alkyl substituted carbon under acidic conditions, in which case the epoxide oxygen is protonated by that strong acid, right, and carries that formal +1 charge. And so maybe we would think this would work. However, that strategy won't work either, because the strongly basic Grignard reagent just comes along and deprotonates that oxygen to give us that epoxide back. So the synthetic traps that we've examined is a result of regiochemistry that prevents us from being able to make the desired product. Now, regiochemistry applies to other reactions too, so keep this type of synthetic trap in mind whenever you propose to use a particular reaction synthesis. And so kind of the take-home message here is always make sure that the regiochemistry of a proposed synthetic step will lead to the intended product. So when we're thinking about synthetic traps, regiochemistry can be a problem, but it turns out we can have more than one problem, right? So maybe it's not just regiochemistry that's our problem. There can be more. So another example of a synthetic trap is presented in the transform proposed here, right? Which undoes the alkylation of a terminal alkyne, right? In the forward direction, that's what the synthetic step would look like, is we would react this with sodium hydroxide. And then this molecule here. The problem is that when NaH is added, the terminal alkyne is deprotonated to generate the alkynide anion. And then in the subsequent reaction, that alkynide anion is intended to behave as a nucleophile and displace that bromine by leaving, right? As shown over here, okay? So we expect it in this dashed line to come in. That's what we want. We want it to come in here and go up here and give us this product. But that's not what happens, right? Unfortunately, what that alkynide anion does is it behaves like a strong base that it is and deprotonates that OH group, right? And so because those proton transfer reactions tend to be much faster than the nucleophilic substitution reactions, this is going to be the main product, and that's not really what you're looking for. So the synthetic trap here arises because there's more than one functional group in the proposed synthetic step. And so what you need to keep in mind is that whenever you propose a synthetic step in a synthesis, check to see if other functional groups can react. Now later, what we're going to find is that we can change this reactant here in such a way that can protect this alcohol group to keep it from reacting. And that's called protecting groups. And they're used all throughout organic chemistry. And we'll talk about those later. But there are some workarounds to this. So your success in solving multi-step synthesis will depend on your mastery of various reactions and your ability to carry out a retrosynthetic analysis. If you do not know the reactions that we have gone over well and can pull them back out, then this is going to be very hard for you, okay? Now, so that means you really need to know what we've done. So you need to know all the reactions that we've done. And then you need to practice these. So developing these skills requires practice. There's lots of end of chapter problems. We're going to work some problems in class. But one of the things that can help you become really proficient is by constructing your own synthesis problems and then practicing with your friends. So my suggestion here is to choose a starting compound, right? It should have a relatively small number of carbon atoms and also have a functional group you can participate in a reaction you've studied, right? And then choose a reaction to carry out in the forward direction on that starting compound. Keep track of any relevant reagents and conditions and determine the product. Pay attention to regiochemistry and stereochemistry. Then choose a reaction to carry out in the forward direction again on the major product of that first reaction. Determine the second reaction's major product and keep track of those relevant reagents, reaction conditions, regiochemistry, and stereochemistry. And then continue this process through 2 or 3 reactions. And as you improve with the synthesis problems, you should feel comfortable making these 4 or 5 reactions longer and longer. Then write the synthesis problem and treat the product of the final reaction as the target and ask how the target can be produced from the starting compound. Now, I've written these things here for you. But I want to show you kind of what that looks like. So let's say, right, you're going to start with this and you're like, well, what reaction do I know that this can undergo? Well, I know that I can react it in water and an acid and take the ether and form an alcohol. And then I know an alcohol can react with PBr3, and now we've got an alkyl halide, right? And then I know that alkyl halide can react with a terminal alkyne to form this structure here. So these are all structures where you've taken the product and you've made it the reactant, right? And you've synthesized a new compound. Now, then once you've come up with a list like this, and these are the first couple steps, right? You're going to treat this final product as the target, and you're going to treat this as the reactant, and you're going to ask how to synthesize it from the starting material. So your problem will look like this, okay? And so this is the overall synthesis we just did, but now it's phrased as a problem. And using this procedure to construct these synthesis problems will help you become more familiar with the reactions you've previously encountered. And the more familiar you are with those reactions, the better you'll be able to solve the synthesis problems. To improve your skills even more when it comes to problem-solving syntheses, it's helpful to work with a study partner. Each of you can construct a separate synthesis problems and then swap. And then to solve the problem your study partner gave you, apply the retrosynthetic analysis strategies presented here. And then when you finish, you check with your partner to see if your solution agrees with the reaction scheme your partner used to construct the problems. If your solution does not line up with the reaction scheme your partner used, work together to see if one solution is flawed, or perhaps both are good. Now, one of the things that I always love about this is when students do it, a lot of times they will find shorter ways to make these synthesis. And of course, shorter ways to make these synthesis means that they're cheaper. And so that comes out to be a better synthetic technique. Several years ago, I had two students who were working this, and I would argue they were really excited about the exam coming up because they were going to really do really well, right? And I came up with a problem, and I thought it was a multi-step synthesis, very much where it had 3 steps. And they immediately figured out how to do it in 1 step because there was something that I had overlooked. And so, but they were really familiar with it. And so they did not go the long way. They went the short way, and of course got all the points. But this method just helps you get really, really familiar with these types of problems. So let's do an example of one of these problems. So suppose your study partner that we just talked about constructed the following synthesis, and they gave it to you to solve. Design a synthesis that can be used to carry out the transformation. So the first thing I do is I count the carbons. So there's 1, 2, 3, 4 carbons here, and there's 1, 2, 3, 4, 5 carbons here. So the target's backbone here has 5 carbons, but the starting material just has 4 carbons. So we're going to need a carbon-carbon forming reaction to be used. But at this point, we haven't learned a reaction that'll produce an alkene. Okay, so let's hold on to that for a second. Okay, now, what functional group could be converted into an alkene? So we have an OH here and a Br here, and we're asking ourselves, what could we convert into an alkene here? An alkene can be produced from an alcohol. So when we look at this, right, we say, okay, so we've got 1, 2, 3, 4, that guy, and we know that alkene can be produced from an alcohol. And so the alcohol would look like this. Okay. And so so that would be a dehydration. If we undid a dehydration reaction, right? And then the next thing that we could do, right, is then an alcohol can be a product of an epoxide ring opening reaction that forms a carbon-carbon bond. So when we look at this guy and we think about it, right, we come here and we say, okay, hey, look, there's the 2 and the 3, and so we can kind of cut it here, okay, to make that an epoxide. So when we do that, it would look like this. And then we could use a Grignard, we could use a lithium reagent, we could use one of those to undo that epoxide ring. Okay. And then, right, that's still not gotten us back to the starting material, but the question we could ask ourselves is, could an epoxide be made from the starting material? And so that epoxide looks like that. And so what would we do to undo that epoxide ring formation? And so to undo the epoxide ring formation, we could use if we undid that, we would need a halohydrin, right? So it would look something along the lines of that, right? Which is our new starting material. And so now we can write this reaction in the forward direction using the reagents that we didn't necessarily list. So I'm starting with this molecule, right? And I am going to take it to this molecule. And I know to do that reaction, I need a strong base, so that's NaOH, right? And so that forms the epoxide. And then here, I can add the CH3Li, or if you chose MGBR, any of those. And then I know I'm going to need an acid workup, which is H2O and H2SO4. And then I can get to my alcohol, right? And now I need to think about, how do I go from an alcohol to that double bond? And that's a dehydration. And so I can use concentrated H3PO4, right? And heat. And that's a terrible double bond. Let me do better and get to that product. So practice is really going to be what helps you with this. So do take time and learn your individual reactions and then practice putting these together.